In the last video, I introduced you to the idea of the chain rule with partial derivatives, and we said, well, if I have a function xi, Greek letter xi, it's a function of x and y, and if I wanted to take the partial of this with respect to I want to take the derivative, not the partial, the derivative of this with respect to x. This is equal to the partial of xi with respect to x plus the partial of xi with respect to y times dy dx. And in the last video, I didn't prove it to you, but I hopefully gave you a little bit of intuition that you can believe me, but maybe one day I'll prove it a little bit more rigorously. But you can find proofs on the web if you're interested for the chain rule with partial derivatives. So let's put that aside and let's explore another property of partial derivatives, and then we're ready to get the intuition behind exact equations. Because what you're going to find, it's fairly straightforward to solve exact equations, but the intuition is a little bit more well, I don't want to say it's difficult, because if you have the intuition, you have it. So, what if I had, say, the same function xi, and now I were to take the partial derivative of xi with respect to x first. I'll just write xi. I don't have to write x and y every time. And then I were to take the partial derivative with respect to y. So just as a notation, this you could write as, you could kind of view it as you're multiplying the operators, so it could be written like this. The partial del squared times xi, or del squared xi, over del y, del, or curly dx. And that can also be written as, and this is my preferred notation because it doesn't have all this extra junk everywhere. You could just say, well, we took the partial with respect to x first. So this just means the partial of xi with respect to x. And then we took the partial with respect to y. So that's one situation to consider. What happens when we take the partial with respect to x and then y? So with respect to x, you hold y constant to get just the partial with respect to x, ignore the y there. And then you hold the x constant, and you take the partial with respect to y. So what's the difference between that and if we were to switch the order? So what happens if we were to, I'll do it in a different color. If we had xi, and we were to take the partial with respect to y first, and then we were to take the partial with respect to x. So just the notation, just so you're comfortable with it. That would be, so partial x, partial y. And this is the operator, and it might be a little confusing that here between these two notations, even though they're the same thing, the order is mixed. That's just because it's just a different way of thinking about it. This says, okay, partial first with respect to x, then y. This views it more as the operators, that we took the partial of x first, and then we took y, like you're multiplying the operators. But anyway, so this can also be written as the partial of y with respect to the partial of y, and then we took the partial of that with respect to x. Now, I'm going to tell you right now that if each of the first partials are continuous, and most of the functions we've dealt with in a normal domain, as long as there aren't any discontinuities or holes or something strange in the function definition, they usually are continuous. And especially in a first-year calculus or differential course, we're probably going to be dealing with continuous functions in our domain. If both of these functions are continuous, if both of the first partials are continuous, then these two are going to be equal to each other. So xi of xy is going to be equal to xi of yx. Now, we can use this knowledge, which is the chain rule using partial derivatives, and this knowledge to now solve a certain class of differential equations, first order differential equations, called exact equations. And what does an exact equation look like? An exact equation looks like this. It's always the color picking is the hard part. So let's say this is my differential equation. I have some function of x and y. So, I don't know, it could be x squared times cosine of y or something. I don't know, it could be any function of x and y. Plus some function of x and y, we'll call that n, times dy dx. dy dx is equal to 0. This is Well, I don't know it's an exact equation yet, but if you saw something of this form, your first impulse should be, actually your very first impulse is this separable? And you should try to play around with the algebra a little bit and see if it's separable, because that's always the most straightforward way. If it's not separable, but you can still put it in this form, you say, hey, isn't it an exact equation? And what's an exact equation? Well, look immediately. This pattern right here looks an awful lot like this pattern, right? What if m was the partial of xi with respect to x? What if xi with respect to x is equal to m, right? What if this was xi with respect to x, and what if this was xi with respect to y? So xi with respect to y is equal to n. What if? I'm just saying, we don't know for sure, right? If you just see this someplace randomly, you won't know for sure that this is the partial of with respect to x of some function, and this is the partial with respect to y of some function. But we're just saying, what if? If this were true, then we could rewrite this as the partial of xi with respect to x plus the partial of xi with respect to y times dy dx equal to 0. And this right here, the left side right there, that's the same thing as this, right? This is just the derivative of xi with respect to x using the partial derivative chain rule. So you could rewrite it. You could rewrite this is just the derivative of xi with respect to x. And xi is a function of xy is equal to 0. So if you see a differential equation, it has this form, and you're saying, boy, I can't separate it, but maybe it's an exact equation. And frankly, if that was what was recently covered before the current exam, it probably is an exact equation. But if you see this form, you say, boy, maybe it's an exact equation. If it is an exact equation, and I'll show you how to test it in a second using this information, then this can be written as the derivative of some function xi, right, where this is the partial of xi with respect to x, this is the partial of xi with respect to y. And then if you could write it like this, then you take the derivative of both sides, you take the antiderivative of both sides, and you would get xi of xy is equal to c as the solution. So there are two things that we should be caring about. That you might be saying, okay, Sal, you've kind of you've walked through xi's and partials and all of this. What is it? One, how do I know that it's an exact equation? And then, if it is an exact equation, which tells us that there is some xi, then how do I solve for the xi? So the way to figure out is it an exact equation is to use this information right here. We know that if xi and its derivatives are continuous over some domain, that when you take the partial with respect to x and then y, that's the same thing as doing it in the other order. So we said this is the partial with respect to x, right? This is the partial with respect to x, and this is the partial with respect to y. So if this is an exact equation, if this is the exact equation, if we were to take the partial of this with respect to y, right? If we were to take the partial of m with respect to y, so the partial of xi with respect to x is equal to m. If we were to take the partial of those with respect to y, so we could just rewrite that as that, then that should be equal to the partial of n with respect to x, right? The partial of xi with respect to y is equal to n. So if we take the partial with respect to x of both of these, take the partial with respect to x, we know from this that these should be equal if xi and its partials are continuous over that domain. So then this will also be equal. So that is actually the test to test if this is an exact equation. So let me rewrite all of that again and summarize it a little bit. So if you see something of the form m of xy plus n of xy times dy dx is equal to 0, and then you take the partial derivative of m with respect to y, and then you take the partial derivative of n with respect to x, and they are equal to each other, then, and it's actually if and only if, so it goes both ways, this is an exact equation, an exact differential equation. This is an exact equation. And if it's an exact equation, that tells us that there exists a xi such that the derivative of xi of xy is equal to 0, or xi of xy is equal to c is a solution of this equation, and the partial derivative of xi with respect to x is equal to m, and the partial derivative of xi with respect to y is equal to n. And I'll show you in the next video how to actually use this information to solve for xi. So here are some things I want to point out. This is going to be the partial derivative of our xi with respect to x, but when we take the kind of exact test, we take it with respect to y, because we want to get that mixed derivative. Similarly, this is going to be the partial derivative of xi with respect to y, but when we do the test, we take the partial of it with respect to x, so we get that mixed derivative. But this is with respect to y and then with respect to x, so you get this. Anyway, I know that might be a little bit involved, but if you understood everything I did, I think you'll have the intuition behind why the methodology of exact equations works. I will see you in the next video where we will actually solve some exact equations. See you soon.